Jason, thanks for the invitation, and thank you for everybody for being here. So my talk is going to be on how we're working towards the operationalization of a deep learning model we've developed for Eastern Pacific or strong Eastern Pacific El Niño events in Peru. So it's both to be used in Peru, but with the Peruvian perspective in terms of what the most relevant events are. And it has a very important aspect, which is the explanations, which I'm going to get more into a bit later. And this is work actually led by Gerardo Rivera Tello and with Cristina Caramperido, and now with the help of Jose Obregón here at IGP. So, this is kind of something all of you know about, but just to set the background for what we're doing. So this is what ENSO effects in terms of precipitation would look like roughly worldwide. And I want to just focus on this region. I don't know if you can see my cursor here. Right off the western coast of South America, we have these green anomalies, which are just hitting the northern coast of Peru and the coast of Ecuador. So for us, what this looks like is more like this. So on the left, we have the climatology in terms of precipitation for the December-April period. And on the right, we have what it looked like during the 82, 83 El Niño. And you can see these very, I guess, localized precipitation anomalies. These are not anomalies, this is the absolute precipitation. And you can see the values here are higher than what we actually have even in the Amazon forest. We go from being a coastal desert to a very, very rainy region, which means a total change of the character of climate in this region. And this obviously produces severe flooding and damages to the infrastructure and the population. This is two records we have for the El Niño along the coast of Peru. On the top, and here we have the river discharge between February and April for this location in northern Peru, Piura. If we can see an enormous interannual variability. So we have years in which the river pretty much had no water, and then years like 83 or 98, which obviously correspond to very strong El Niño events. The precipitation was and river discharge were huge, comparably, as I said, to the Amazon. Now, if we see the record on the bottom here, we have SST, surface temperature, and also along the coast of Peru. We also have very strong variability. And obviously, as we would expect during these strong El Niño events, we have very high temperatures. You can see the range of SST going from 16 to roughly 26, or roughly 10-degree range between low and high. One thing I wanted to show or talk about a bit more, is that even though we know that these two big events, 83 and 98, which had SST anomaly patterns that like the ones we see on the left, we were very warm along the coast of Peru, extending all the way into the Central Pacific along the equator. We also had in 2016 this event, which was also a very important Niño globally, which had a substantial warming along the coast, but in terms of precipitation or river discharge, it was pretty much normal, even somewhat dry. And this event is something we can tell here we worked on, trying to understand from the perspective also of prediction, but also to some extent of the impacts. And we can see down here how the precipitation anomaly patterns were very different between the 97, 98 El Niño, which featured this very rainy anomaly along the coast of Ecuador and Peru, whereas in 2015-16, it was pretty much dry everywhere. And even though we had a warming, now I'm going to the top right plot here, in which we're comparing the Niño 1+2 SST anomalies in the Far Eastern Pacific. If we focus on this pink band here, which corresponds to the rainy season along the coast of Peru, we see that the warming in 2016, which was substantial, was roughly the half of what we saw in 97 or 98 or 83. So it was warm, but it was not nearly as warm as we had in those years. On the other hand, if we look at the Central Pacific, specifically Niño 4 region, we see that 2015 was actually the warmest compared to the other events. So just by looking at this, we would say the patterns were quite different between the 83 and 98 versus 2016. And this for us has very direct impact in terms of how climate changes in our country. We've already, for the past few years, been working in the community towards understanding better the diversity of events, the ENSO events, either from the perspective of the patterns, like we were saying, whether the warming is larger in the Central Pacific or the Eastern Pacific, which is, I guess, the most common way of classifying these events. Also, we could classify them in terms of the strength, whether they're very strong or moderate. But as we'll see, just the pattern itself is very important for us in Peru, particularly because if we look at how say the most common Niño index, which is Niño 3.4, correlates with precipitations in our country, we would have during El Niño wet conditions in the north and coast of Peru, and dry in the southern Andes. But this is a mixed signal because it's not just ENSO producing always this pattern. If we now look at what the warming in the Central Pacific would do in terms of precipitation effects in Peru versus the Eastern Pacific warming, we can see that these two regions have very different impacts. The Central Pacific warming leads to a drying along the Andes region in Peru, whereas the Eastern Pacific warming leads to wet anomalies in northern coastal Peru. So what we see when we say correlate Niño 3.4 variability with precipitation in Peru is a mixture of these two effects. These are associated very different spatial patterns. So in order to determine whether we're going to have one or the other or a combination of these, we will need to predict the actual pattern, how much of the Central Pacific warming versus how much of the Eastern Pacific warming we will have in a particular event. Only then we could be able to say something about what precipitation anomalies might look like. Well, these are those two patterns I showed have these time series, which are very different from each other for the Eastern Pacific and the Central Pacific because they are based on principal components, which by construction are orthogonal, uncorrelated. They clearly show us that in 1998, the warming in the Eastern Pacific was huge compared to the Pacific warming, but in 2016, the Central Pacific and the Eastern Pacific warming were kind of comparable. Very different events in that sense. Now, in terms of forecast skill, we have many models available, like from NMME or the Copernicus example. They're quite good at predicting ENSO in general, as measured, for instance, by Niño 3.4. Here in this plot, what we're showing is the correlation, anomaly correlation between the predicted and observed indices for different lead times and target months. And essentially, what I want to focus is on the area here above 0.7 correlation, bounded by this yellow line here. So we see that for Niño 3.4, the predictive skill is quite high. For the C index in the Central Pacific, it's also not that bad. But for the Eastern Pacific, it's not good at all. So we have very, very limited predictability if we now focus on the individual patterns. So roughly speaking, say first mode of variability, the ENSO pattern, broadly speaking, is adequately predicted by these models, but for the specifics of the patterns, now we have much more limited predictability, perhaps with a lead time of around a couple of months. So this is a challenge, obviously, for us. We would like the skill for particularly for the E index, which is directly connected to the severe flooding and rainfall in the coast of Peru, to extend that lead time as much as possible. Now we know for the extreme El Niño events in this Pacific, here's we have a composite from the GFDL CM 2.1 model, which does a roughly good job in representing these extreme events. And we have the 83 and the 88 events also shown here. So we see that the Eastern Pacific warming that tends to have a peak around January that is preceded by positive heat content anomalies, also by by anomalies in the Central Pacific, warming in the Central Pacific, and also by westerly winds in the Central Pacific. Yeah. So in terms of useful predictors, we could say, well, this heat content, positive heat content, is somewhat weak as a predictor. The same with the surface warming in the Central Pacific. But the westerly wind anomaly in the Central Pacific seems to be more robust in terms of how different from zero it is in the whole ensemble of CM 2.1 model events. But still, I mean, we want to move from this to a predictive prediction model. We will need to establish more quantitative relationships. And one thing we found is that precisely if we look at the August value of this Central Pacific westerly wind anomaly, we had a very strong relationship between the value of that index versus the probability of the E index, the Eastern Pacific warming, from being as high as we saw in 83 or 98. Here, the red dots are observed values, and the gray dots are the model simulations. So they all line up pretty well, and it may give us some confidence that this might be a useful predictor. Obviously, here, I mean, we published this in June 2015, and the data was pretty much all up to that date. But in that year, we also had the 2015-16 events, and from then onwards, we could compare how this method would have worked out. So we see that the 2015 event, 15-16, did have a strong westerly wind index, but the warming in the Eastern Pacific was not as high as in 98 and 93. So we could say that it was within the error bars, but it's still, I mean, this overestimation, I would say, of the possible impact of the possible warming, say, strongly affected the final impact in terms of precipitation. This year, on the other hand, we're 0 here, so using this scheme, we will not predict any possibility of a strong Eastern Pacific warming this coming austral summer. Okay, so now that after that long introduction, what we would like is to know what are the actual precursors, the skillful predictors of El Niño in the Eastern Pacific, and how to use these for more skillful actual predictions of this type of events. So what we've done is we've developed a deep learning model, which uses a global SST heat content. Well, it's sea surface height instead of heat content, and surface winds from GCMs or reanalysis to produce skillful predictions of E and C, the two indices in nature, and use the explainable AI techniques to identify those sources of predictability and guide scientific understanding and the assessment of the forecasts. So this is what we've actually done. I'm not going to go into any details about the actual model, but the basic idea is that we input the observed fields of sea surface temperature and sea surface height, zonal and meridional wind for the 3 months leading up to initial conditions, so say up to now. And we get as a result, as the output, prediction for the E and C indices for the next 12 months, and also the probability of the E index to exceed this threshold of 1.5 in January, which is a proxy, say, for strong El Niño events in the austral summer. And we have, this is the architecture, which we adapted from the Ham et al. Papers in 2019, 2021. We have 30 versions of the model. So these were all trained in the same way, but with different, say, initial conditions in the random initialization of the weights. So it's pretty much an ensemble of models with the same architecture and same data training. And yep, and this model is well, it's actually, this work is currently under review. We have good expectations that it's going to be published soon, hopefully. Okay. So one issue we've been very careful with is the problem of data leak. Is that there is a crisis in machine learning science, in that there's many studies that look too good to be true, and they're actually too good to be true. And there's a whole set of different types of problems in these studies that essentially it's, I would summarize as testing or validating the model with the same data which was trained. In the end, it's kind of the problem of having independent validation. So there's a contamination of the testing data sets with the training data sets. And this is something I would say in a climate empirical studies, we have not really been looking at very carefully generally in the community. But for the machine learning community, this has, in a bunch of different fields, this has been shown already to be a problem. So we've been careful at trying to not fall into this error. So the way we've done it, we've developed the model, say the foundation or the base model, with CMIP6 simulations. So these are just climate models running freely under historical forcings. We selected the 16 best models in terms of ENSO diversity. So there's I won't go into any details about that, but it represents the nonlinearities of between the Eastern and Central Pacific variability. We have over 6,000 years then for the training. And for this development, we've actually divided the data into actual training data set that goes into the determination of the model weights. This is what we call DEF1, development 1 dataset, which we use specifically for the early stopping within the training itself. DEF2 is what we use to compare among different versions of the models and select what the best version of the model we're going to keep. And test would be just for getting some measure of the actual skill of that model. And I should emphasize that for the training data, we've tried to balance the number of strong El Niño events in the datasets with all the other, because we're mostly interested in getting the strong and Eastern Pacific El Niños right, and because of by definition, their extreme events are rare. We wanted to give more data to the model training in order for it to pick up the skills it needs to break these models better. So it's biased. I mean, the way we've trained the model is biased towards those events. Then once we've selected the best model based on CMIP6 data, we then proceeded to fine-tune the model with observational data from SOTA from 1871 to 1985. So this includes the 1877-78 strong El Niño and the 1983 strong El Niño as well. Once we did this, and we just did not look at all what was going on, we did not do any additional tuning of the fine-tuning procedure. We validated with or verified this with independent data sets, which was from the GODAS database from 1990, which in 2022, which includes the 1998 events, the 2016 events. So this period was not even looked at. This dataset was not even looked at during all the previous steps. We didn't run the model. We didn't. We had it in the lock and key until the model was set. The fine-tuned model was set. And and I mentioned the issue of explainability, and this is particularly important. And this is from the recommendation from UNESCO, that for applications, AI applications that can impact the end user in a way that is, I would say, permanently and high risk, like in the case of predicting extreme events that can produce damages and loss of lives, we need to provide meaningful explanations. And in this case, this means that the AI forecast of the high impact El Niño should be provided with explanation. And not just for the user, which may be the public, but also for the forecasters that are going to be the immediate users of this of the output of this model, who are going to use this as input for their own assessments and produce what in Peru would be the official forecast from the ENFEN Commission. So what we use is the LRP comp method. Again, I won't go into any details. I'm not the expert on this, but this appears to be a pretty reliable technique for identifying what in the input was relevant for the prediction, in this case, of the extreme or strong El Niño event. So just as an example, we have here the zonal wind anomaly in shading, and the red contours are indicated what regions in this variable were most relevant for the prediction of a strong El Niño in the Eastern Pacific. So in this case, it would be westerly winds in the central western equatorial Pacific and easterly winds into a little bit to the north in the Eastern Pacific. So this is what the model was looking at in this case to enhance the probability of a strong El Niño forecast for the next austral summer. If we had any blue contours here, that would be opposing to the probability of strong El Niño events, but we don't see this example. Now, our model, in terms of this lagged or for anomaly correlation for different leads, it fared quite well compared with the GEM5 NEMO model, which is one we selected because it had somewhat good scale for the Far Eastern Pacific and better than just taking persistence. Still, the model and all models are better for the C index in the Central Pacific than for the E index in the Eastern Pacific, which is still an issue we need to see if we can improve on. But the correlations do not really address the issue of whether the model predicts well the strong events. So here, the two main cases we have in the testing data set, which is the 1997-98 event and the 2015-16 event. So this, in terms of the E index, if we look at the forecast initialized in May, we had the model, which is in light blue, and in terms of the 30-member ensemble and the dash blue line, which is the ensemble mean. It did a pretty good job in predicting the growth of the event and almost getting the peak right. The orange lines, on the other hand, are the GEM5 NEMO model, which was also pretty good, although the onset was somewhat delayed in terms of how high it reached in late 1997. For the C index in the Central Pacific, I would say our model was somewhat underestimated, but still the observed was within the range of the ensemble. And the NEMO, GEM5 NEMO model was somewhat overestimating it in terms of Central Pacific. In general, I mean, it seems the models did fine with this event. For 2015-16, again, the E index was relatively well predicted by both models, and particularly noting that the 97 and 98 event was much warmer in the Eastern Pacific than 2015-16. So the two models, the AI model and the GCM, were able to predict the difference between these two events. However, for the Central Pacific, our model did not predict the warming we saw in that year, whereas the GEM5 NEMO model did. This is an issue we did not really expect, but now in hindcast makes somewhat sense because we really biased the training toward the Eastern Pacific. On the other hand, our training stopped in 1985, and it was in 2000s that the Central Pacific events were more prevalent. So perhaps the model just was not exposed enough to this type of Central Pacific warming events, so didn't know better. That is something we're going to be testing soon. So in terms of skill scores, We have a critical success index of 0.67, but our testing is so small that it makes more sense to look at the specific cases. So we had 2 true positives in 97 and 2015, which we already saw, but we had a substantial false positive in 2002, which wasn't a strong Eastern Pacific El Niño. So we're going to be looking at these 3 events. And this is what the explanations, the LRP explanations showed us for those 3 years. We're only focusing on May initial conditions. So the first column is 97, 2015, and then 2002. So for 97, 2015, the explanations are quite similar. We had a surface warming in the Far Eastern Pacific in May. We had a increased sea surface height associated with Kelvin waves and the tilting of the thermocline. We had the westerly winds, wind anomalies along the Equatorial Pacific, particularly strong in 97, somewhat weaker in 2015. And we had convergence of meridional winds in the Eastern Pacific, indicating that the atmosphere is responding to the surface warming. On the other hand, in 2002, we had pretty much nothing really going on, perhaps a little bit of westerly winds. And it's just not clear for us at all why the model decided to predict a strong El Niño event in that case. But I guess that the take-home message here would be, as a forecaster, if we have access to this information, which we do, as the forecast is made, we can assess whether we can trust the model or not. So for these 2 cases, 97 and 2015, it's pretty clear why the model is predicting strong El Niño. For 2002, we could just say, well, this does not look right. We could just dismiss this focus. Now, by the time we prepared this paper, we were working with the May initial conditions up to the May initial conditions for this year, 2023. So this is the forecast we made with that data. So essentially, it was already warm in the Eastern Pacific here at the top, and the model predicted the maintenance of those anomalies up to next year and then decrease. And for the C index, a small continuing warming to reach a small value and then slowly decrease. And the reason for this kind of mild forecast is that what the model was seeing in this is March, April, and May was primarily the ongoing coastal warming, which we had actually since February this year. A little anomalously high sea surface height on the Western Pacific, which is something that has been seen to be relevant as a potential predictor of El Niño, particularly the off-equatorial sea surface height here to the south of the equator. But pretty much nothing else in terms of westerly winds, which is something we're still seeing now. And nothing as obvious also in the meridional wind. On the other hand, an interesting feature of this event so far is that in the northern tropical Atlantic, we have warming that the model is highlighting as opposing the probability of a strong Eastern Pacific El Niño. So this is, for the model, this is providing some negative prediction for the Eastern Pacific El Niño. And this is something that's up to this day, it's still persisting. Yeah, actually, this is for September initial conditions. This again, the model is predicting the maintenance of this anomalies and then decreasing towards next year. And the same with the C index. And here the predictors are much stronger in terms of Eastern Pacific warming, extending to the Central Pacific. But again, the other variables, sea surface height and zonal wind, are not really there. Meridional wind, we have some convergence in the Eastern Pacific, which is indication of some atmospheric response in the Eastern Pacific, but we're not getting that zonal wind response that we saw in 97, 2015. On the other hand, as I mentioned, we'll still have this negative contribution from the northern tropical Atlantic. And one thing we're working then towards now is that given that underestimation of the Central Pacific warming, which could be, as I said, perhaps due to the bias in the training, but also in the fact that the Central Pacific events were more common later in the period. But we're going to be trying soon, or we're actually starting already, is fine-tuning the model now up to more recent year, 2009 in particular, so that this would include, for instance, the 2010 Central Pacific El Niño. There's different ways of doing the fine-tuning so that we can then make this an operational procedure. So every year, perhaps we will be updating the model with the latest event or latest year of data. And once we have this strategy figured out, we would then proceed to have an updated model all the way up to 2022 or 23, sorry, and use that for operational predictions. And I think that's it. Yes. So in summary, we've developed this skillful deep learning model for insect diversity and probability of strong Pacific El Niño, using sea surface temperatures, sea surface height, and surface winds from climate models and fine-tuning with observed data, and having great care to avoid data leakage. We have the explainable AI that allows the humans to assess the forecasts and provide extra guidance. So we could actually use, even if the model itself were not more skillful than the GCMs we already have, the GCMs do not explain themselves. So just having explanation from this model would be useful for forecasters to assess also the GCM predictions. And then we would expect, although we do not know for sure, that doing a regular fine-tuning of this model with more recent data should at least allow the model to maintain the prediction skill given that the climate is changing, but perhaps even increasing that skill. So that's kind of what we're going to be testing, but more from an operational perspective, and that is something we will then figure out a few years from now. So that's it. Thank you.
Hi, Ken. Great talk. Thanks for that. It's super interesting to see this model and both how you've sort of developed the explainable component of it. I was wondering, is there when you're showing the dampening influence of the North Tropical Atlantic, and also in September, it was highlighting the North Pacific as counteracting the development of the El Nino there. Do you think that those are physically realistic mechanisms? And if so, what might they be? And if not, is there a way to modify the forecast model itself to remove those influences and see how that would affect the forecast itself?
Sorry, thank you. No, yeah, with respect to Northern Atlantic warming, I don't remember the papers now, but there's quite a few talking about the negative influence that warming has on the development of El Nino, or actually the cooling on La Nina. But the North Pacific warming, I don't know if there's any research that would point to this effect. So we're also kind of selective with the way we use to interpret the explanations, because not always the explanations are going to show something physical, because the training of the model itself might be somewhat, let's say, it could have made the model learn some noise, not just true signals. So we still have to use our physical knowledge to be able to assess whether the explanation makes sense. And that obviously helps us determine whether a forecast makes sense. So the North Tropical Atlantic warming, that makes sense. I mean, the mechanism I don't remember, but for instance, I think there's rossby waves propagating through the tropical atmosphere and from the Atlantic to the Pacific, inducing easterly wind anomalies. But for the Northern Tropical Atlantic, Pacific, sorry, nothing as clear is known. And if we go back to, I think it was here. Yeah, so I didn't show or talk about in this plot here. We also see in the Northern Atlantic, now not tropical, but North Atlantic, something that kind of looks like NAO, but we just don't know of any physical effect from that region to tropical Pacific. So we're still flagging it as perhaps a spurious feature for the model prediction. Did I answer all your questions? I think there was something else, but I kind of forgot.
I mean, that answered most of them. The only other part I was wondering is if within the model, if you could do something,
yes, the experiment,
replace that or remove that influence that you think is spurious. And I mean, I obviously maybe you wouldn't want to do that at all, but I was just curious if you had thought about that.
Yeah, that's a good point. Actually, we did at some point think about it. We didn't just go. We have time to go through, but it would be a pretty simple thing to just test by surgically editing the anomalies and see how much of an impact that makes. It'll be interesting to see.
Thanks.
Thanks, Ken. This is great. I see you use the architecture of Ham et al. So what I was curious to know, you use the T-3 maybe, yeah, past 3 month observation. Did you like get some testing on if instead of past 3 months, if I use the past 5 years of the data, does it improve the skill or not?
Sorry, can you repeat the last part? I didn't
So,
get it. Did we try both?
Yeah, so in this case, your look back period is T-2, like past 2 months of the data. Instead of past 2 months, if I look back at past 5 years, that it gives you a better prediction skill. Why or why not?
Yes, we didn't actually test that. We were somewhat worried that even though we had what was it, like 6,000 years of data in terms of extreme El Niño events, we wouldn't have enough. So we didn't want to increase the number of parameters of the model too much. So we didn't actually test that. We did try different combinations of layers and number of neurons, I guess, in the model, but we did not try that specifically.
Thank you. Hello. This was an excellent talk. Thanks so much for sharing this work. I was curious if you could go into a little bit more detail about some of the architecture choices and most specifically the outputs. So I see that you're outputting multiple items, and so I was curious what the reasoning was for that. If you found that made training more stable, or is it just because that's really all the items that you needed for your operational purposes? And then I'll sneak in one more in there, which was about explanations and how you might be thinking about these variables and their correlations, both temporally and across, SSTs, SSH, wind. They are correlated, and so that might influence your explanations that you're looking at. So those two questions. Thank you so much.
Yeah, thanks. So regarding the details of the architecture, I'm not the best person to ask. I think Gerardo didn't make it to the talk. But we essentially adapted the Ham et al. Architecture. And one of the outputs that we have here, which I didn't mention at all, is having the month of the year as output, which was physically very weird for us at first, but it seems to work better in terms of how to incorporate seasonality in the model. We did try to use seasonality as an input, but it seems to work better as an output. It really doesn't make much sense to us, but at that point, we just decided to go with it. So that's why we have that as an output. That's what I think Ham et al. 2021 did. Now, regarding the other more physical, I guess, outputs, we have 3 types. We have 2 regression outputs, which are the ENC indices for next 12 months. And we have the probability of a strong El Niño, which we could derive in principle from the E index. But we had it separately pretty much because of 2 reasons. One was we thought that could be a way of emphasizing the training process to get the extreme strong El Niño events better, which we then determined it didn't make much of an impact in that sense. But the other reason is that we use this output for the explanations. So the XAI technique is applied to the classification output, not the regression output. It just made it much easier for us to be able to interpret the explanations, because if we did it with regression, it was just more complicated for us to understand. So that's why we had this classification output. Otherwise, the regression output should have been enough if we just cared about the prediction.
Okay, thank you.
Oh, sorry. I just remembered the other part of your question, which was the correlation between the predictors. So yeah, that is something that in principle we expected to see more, but in practice, the model seems to distinguish between, say, SST and sea surface height. So sometimes it does, even though it might have a signal in both, it will only emphasize one, like in this year with the sea surface temperature anomalies in the Eastern Pacific. So I think even though there is strong correlation between the variables, they do provide independent information that the model is picking up.
Yeah, hey Ken, that was very interesting. I was curious for a couple of reasons. If you had looked at the version that you just trained on the models before you did the transfer learning, for a couple of reasons. One, I'm wondering if actually that scale was no worse than the transfer learning scale. In other words, did the transfer learning actually improve things, or is it the case that you don't have enough data, which I've seen in other contexts, to actually correct your model of your models to make it more realistic? And related to that is this issue of, false positive, because you have this 2002 event, which when I look at it, it's not immediately obvious to me why you're saying you would have rejected it based on the XAI. I mean, I can see in retrospect, because we knew there wasn't a 2002 event, that we would reject it. But that hindcast bias is really going to be hard to overcome, I think, when you look at this. Whereas if you were to look in the models and ask, if you had some independent test of model data, if you were to do the same thing, you wouldn't have that bias, right? You wouldn't know in advance. You could look at all the cases where it's predicting it and look and say, okay, if I'm treating this operationally, would I have looked at this and said, yeah, I believe this or not? And then you can see whether or not it occurred. And at least that would give you some sense of whether this is giving you that information, or whether you can't actually differentiate when the model tells you an event's going to occur. It's too hard for you to figure out based on this information whether you should believe it or not. That's all kind of it's one very large question, but it's all basically the same root of just looking in the model training itself before you even do the transfer learning. Unless the transfer learning gave you such a huge boost that you wouldn't consider that.
No, thanks. No, that's a good question. And actually, so starting with that, the issue of the training. So we were very concerned about the data leakage. So we wanted to be strict with our protocol. We didn't want to be like correcting after, that hindcast bias you were just mentioning. So we did not want to go back. So we determined that we were going to first train with CMIP, and then we were going to fine tune, and that would be our model. So we didn't peak. We didn't look at what would have been the case if we hadn't used the fine tuning. I don't know if that makes sense. I'm sure Gerardo didn't peak, but I personally did not peak. I did not want to see
if it would be better. You can look
after the fact. Yeah, I could peak now. I just haven't. So unfortunately, Gerardo is not here, but I think he did peak. But regarding the other part of your question, so I mean, just from the forecaster perspective, if I had been in 2002 looking at this output, this input, for the model, in which I, as a forecaster, would see nothing going on, I mean, in terms of anomalies, not the AI part, just the anomalies. There's nothing obvious that would tell me there should be a strong El Nino in the Far Eastern Pacific next coming summer, austral summer. And I would believe the model more if it pointed to something that were substantial and made sense physically. But all the LRP method showed here was this little bit of westerly anomaly here in the Western Pacific. And I personally wouldn't believe it. I wouldn't say, well, yeah, this makes sense. This was going to grow into big El Nino next year. So when I say I would reject it, I mean, based on my own personal experience in forecast, I would say there's nothing here that would support that forecast, which is totally different from the case of 97, 2015. In these cases, it's very obvious. And the model is saying, well, this is what I'm looking at. You know, I know this makes sense from the answer perspective. So that makes it much more trustworthy, I guess, in 2002. But obviously, that's a personal call. Other people might have different interpretations of this.
But then does it contribute? I mean, is the machine learning actually teaching you something? I think that's kind of the question here is if you're using this in an operational context and you're making decisions you would have made independent of the machine learning, and if the machine learning is actually a worse skill model than say, the Gen 5 Nemo, what do you gain here?
Yeah, so that's what I was saying in the beginning. Even if the model skill were not good, just having these explanations is useful for the forecaster. It allows us to focus on features that might have skipped our mind at the time of the analysis of the observed in the GCMs, because GCMs provide none of this information, right? So at least this is more transparent in that sense. Even though people say that AI models are black boxes, GCMs are worse because they do not have this. So at least this allows us to peek under the hood and see what's going on within the model. And obviously, I mean, the models, any model can fail. At least this gives us some elements to assess whether that specific prediction is something we could believe on. But again, this is a judgment call in the end by the humans. No, this forecast would not go published automatically. This would have to go through humans to be incorporated in the official forecast.